So what I want to do before we jump into the examples themselves is I want to look at the video example from page 6. So this is in the second video. So this is part of 6.2. And so I want to talk through this video example just because there were some questions on why we manipulate these equations differently than when we used Hess's law and when we manipulated delta H. So on, let's see, there it is, page 6 of the notes. This is kind of halfway down. So let's consider the reactions below, and it gives us reaction 1 and reaction 2, and it gives us the K expressions. So they already wrote the K expressions for us. Products over reactants. Products over reactants. Then it says, which of the following expressions would allow us to calculate the equilibrium constant for the following overall reaction? So here is the overall reaction that we're trying to get. So the first thing that we need to ask ourselves is, how do we need to manipulate these equations to get this overall reaction? So before we even focus on doing anything with the K values, right, with the K expressions, let's just focus on how we need to manipulate reaction 1 and reaction 2 to get this overall reaction. The manipulation is just like Hess's law. So if I take a look at reaction 1, look at what is kind of one of the more unique substances. So for me, I looked at NOBr. I noticed that there were 2 NOBrs as the product of the overall reaction. Well, I noticed that there's just 1 NOBr here. So what I need to do is I need to take this entire reaction and I need to multiply by 2. So it becomes 2, 1, 2. Right, again, I'm not going to worry about K yet. We'll look at how to manipulate K in a second. For reaction 2, well, I don't see NO anywhere in here, so I'm not going to look at that. But I do see that N2 and O2 are reactants in this equation. I need N2 and O2 to be reactants in this equation. So I need to flip the reaction. And if I flip the reaction, it becomes N2 plus O2 is at equilibrium with 2NO. And then what I notice is that the 2 NOs will cancel. I have N2O2Br2 at equilibrium with 2 NOBr. So I've manipulated these 2 equations so that when I add them together, they become this overall reaction. Now we need to look at how this manipulates K, because we're not just multiplying anymore. K is not about multiplying to change your coefficients. Let's look at what this does. If I want to write this equilibrium constant expression, this new equilibrium constant expression, I'm going to have, write it over here. I'm going to have the concentration of NOBr squared over the concentration of NO squared times the concentration of Br2. So look at how these are different. Here was my original. Here's what happens when I multiply the reaction by 2. I'm no longer just multiplying. I can't just do 2 times K. Notice it's NOBr squared now. NO squared. So what we actually do, right, when we multiply a reaction by a factor, you take the K to that factor. So I multiplied by 2, I'm going to do K squared. Because that's how you're changing the K expression. If I look at what happens when I flip this reaction, it becomes the concentration of NO squared times the concentration of N2 times the concentration of O2. Well, look at how this new K is different from this one. It's the reciprocal. So when you flip a reaction, you take the reciprocal of that. So now we know that we have k squared and we have 1 over k. Right? So I know I have k squared, so I'm going to cross out a, I'm going to cross out c. Now it just becomes, how do we put those two, how do we combine those k's? If I write the new expression for this overall reaction, N2, O2, R2. There is the equilibrium constant expression for this new overall reaction. Well, if we look at these two k's, adding them together, if I try to add these two, when you add fractions, you have to make the denominator the same, right, in order to add them together. But if I multiply them, look at what we get. Oh my, that's a bracket, that's fine. So NO squared cancels. One's on top, one's on bottom. When I multiply them together, we have NOBR squared over N2. Oh, this isn't O2. There we go. N2O2BR2. So when you combine k's, it's all about exponents, reciprocals, and multiplying them together when you want to combine the k expressions. So for this video example, this was looking at how. These are very common multiple choice questions because they don't require math. They just require manipulation. So there were a lot of questions on this example, which is why I wanted to make sure that we went through it. Some things to keep in mind for mastering. I was going through mastering, and as we go through the examples, we'll go back through the different example numbers, and I'll tell you which ones are similar to questions on mastering. There are some that are very similar. Other ones will still help. And we'll look at that as we go through the examples. But something to keep in mind for mastering. This was an equation that was discussed in video 6.1. You will not be assessed. So I'm not going to ask you questions on quizzes or on tests on converting between KP and KC. I will not ask you questions on quizzes and on tests for converting KP and KC. However, some of the questions, some of the parts of the mastering questions will still ask you, here's KC, what's KP? So you still are going to have to use this equation, and so I wanted to put it up on a slide just to remind you what each of these variables are and how you can convert. So if you want to convert between KP and KC, KP is the equilibrium constant that is related to pressure, KC is for concentration. And so if you want to convert between the two, you use this equation, and this was in the notes. KP equals KC times RT to the delta N. R is the ideal gas law constant, 0.08206. So always 0.08206. This is actually derived from the ideal gas law. That's why we're using 0.08206. T is temperature in Kelvin. Has to be in Kelvin because R is liters times ATM over moles times Kelvin. And then delta N, that's what is down here. Delta N is moles of product minus moles of reactant. But the most important thing is that you're only focusing on the gases. So it's moles of gas in the product minus moles of gas in the reactant. So they have to give you a balanced equation. And you're doing products minus reactants. We've seen products minus reactants a lot. So for delta N, N is the variable for moles in the ideal gas law. So you're going to look at your balanced equation, take your number of moles, just use your coefficients, number of moles of product that is a gas minus the number of moles of reactant that is a gas. That lets you convert. Notice the parentheses though. It's R times T. It's this quantity raised to the delta n power. Delta n could be positive, negative, or 0. There's no difference, your delta n is 0. If there's no change in number of moles, this equals 1 and Kp equals Kc. But I did want to just bring this back up because mastering will ask some questions on it. You will not see this on a quiz or a test, though. All right, AP no longer tests on the conversion between Kp and Kc. So example 7, right now we're flipping back to the examples within the notes. So back to page 12. Back to page 12. And this is an equation that we're going to look at how we can manipulate K values. So at 1000 Kelvin, Kp, so P just means we're dealing with pressure. So it's always important to just make sure that you're reading, whether one's Kp or Kc, the values are different, but they're calculated the same way. They're just different types of equilibrium constant expressions. So Kp is 1.85 for this reaction. So typically the way that you'll see it written is like this. You'll have the reaction and then you'll have your K written off to the side. So part A, what is the value of Kp for the reaction SO3 at equilibrium with SO2 and 1/2 O2? So we need to think about what do we have to do to the original equation to get to this one. So if you take a look at it, the only thing that I notice is different is that it's flipped. The reaction is flipped. SO3 becomes a reactant, the reactants become products. All right, we flipped the reaction. So we flip the reaction. Let's do this over here. Flip equals reciprocal. Flipped equals the reciprocal. So that means that this new equation would be 1 over Kp. 1 over 1.85. Because when you flip it, just look at the expression. It goes from pressure of SO3 over pressure of SO2 times pressure of O2 to the 1/2. Then it becomes pressure of SO2 times pressure of O2 to the 1/2 over pressure of SO3. The Kp expression is flipped. So 1 over 1.85, 0.541. That'd be 3 sig figs. No units. Doesn't matter whether it's Kc, Kp, equilibrium constants don't have units. Part B, what is the value of Kp for this reaction? So I'm going to go back to the original. Look down to this one. But what did we do to the original to get to this one? It's like we just multiplied it by 2. We multiplied by 2. Now remember, when you multiply, right, so multiply reaction, that factor becomes the exponent. So if we doubled the reaction, we multiplied everything by 2, becomes Kp squared. Again, if you're not sure, write the K expression. It goes from pressure of SO3 to pressure of SO3 squared on the top. You're squaring that value of K. So 1.85 squared to 3 sig figs, 3.42. So when you are manipulating K, you're using reciprocals, exponents, and then if you want to add 2 reactions together, you're multiplying K. Okay, so that's looking at how we can manipulate equilibrium constants. So then we're going to look at solving again. So solving for the equilibrium constant expression. All right, so example 8. This is at the bottom of the page. So gaseous hydrogen iodide is placed in a closed container where it partially decomposes. They give us the equation. So they already give us the balanced equation. At equilibrium, that's very important. At equilibrium, it is found, and they give us the concentrations. So at equilibrium means that all of these concentrations are equilibrium concentrations. Equilibrium concentrations are the ones that you have to plug into the K expression. So it says, what is the value of Kc at this temperature? It is going to be a very good habit to write the K expression first. So when I say write the K expression first, write the Kc expression without numbers. So Kc means concentration. These are all gases. I can include them all in the expression. Concentration of H2 times concentration of I2 over the concentration of Hi squared, because of that 2. The reason that I say it's a really good habit to write the expression first is because sometimes on free response questions, they give you a point for having the expression, even if they don't outright say, write the expression. So only equilibrium concentrations can go into the K expression. Well, this says at equilibrium, so we can actually plug all of the values in. H2, 4.79 times 10 to the negative 4th. I2, 4.79 times 10 to the negative 4th. Hi, 3.53 times 10 to the negative 3rd. Don't forget to square. Hi squared on the bottom. Don't forget those exponents. So if we plug it in, 4.79 e negative 4 times 4.79 e negative 4, 0.0184. And they could go on and they could ask us, what is favored at equilibrium? Or what do we have more of at equilibrium? Well, since this is less than 1, that means that we have more reactants at equilibrium. So since K is less than 1, we actually have more Hi at equilibrium. So that's just plugging in, solving for Kc. We look at example 9. So again, similar. They give us an equilibrium expression, or an equilibrium reaction of NO and Cl2. It says its equilibrium is established. Equilibrium mixture of the 3 gases. So an equilibrium mixture, that's important because that means that we've reached equilibrium. At the end of the week, we're going to look at what happens if we're not at equilibrium. So an equilibrium mixture of the 3 gases has partial pressures, 0.095, 0.171, and 0.28 for NOCl and NOCl respectively. So here's NO, here's Cl2, here's NOCl. Calculate Kp. Okay, Kp. Start by writing the expression without any numbers first. These are all gases, so they can go right into the Kp expression. Pressure of NOCl squared, there's a 2, over the pressure of NO squared times the pressure of Cl2. The coefficients become exponents. Once you have the Kp expression written, then if you have the equilibrium values, you can plug them in. Because it's Kp, you have to be plugging in the partial pressure. Well, they gave us those partial pressures at equilibrium. So NOCl was 0.28. Don't forget to square. That's why writing the Kp expression is also useful. You can see what your exponents are. NO is 0.095 squared times 0.171. Oh man, 2 sig figs. So in your calculator, make sure that you're squaring what needs to be squared. You're using parentheses. I plugged it into my calculator just like this. I got 50.8. So if you use 50.8, that's okay. Usually as long as you're within 1 sig fig, you're okay. Technically, if you round to the least number of sig figs, it'd be 2 sig figs, which would round it to 51. Now, we could, again, answer the question, what is favored at equilibrium? What do we have more of at equilibrium? Well, since K is greater than 1, we have more of what's on top. We have more products. So we would have more products at equilibrium. Any questions before we get to the next one?
I probably missed this in your videos, but how do you determine the product if the arrows go either way?
So we are just assuming the way that it's written is reactants at equilibrium with products.
Oh, okay.
So that's just kind of the assumption that we make. Based on how it's written, we're saying reactants are at equilibrium with products. So when we're talking about reactants and products, reactants will always be what's on the left, products will always be what's on the right, even if it's at equilibrium.
I remember you saying that.
Yeah, yep. Any other questions? Okay, so this next example, we're going to look at what happens when we don't have all of the equilibrium information given to us. So what happens when we have to solve for equilibrium? So I'm going to make sure this is all erased. And in this video, we're going to talk a little bit about ice tables. We're going to start using ice tables a lot with equilibrium. So in this example, it says a mixture of NO, H2, and H2O is placed in a 1 liter container at 300 Kelvin. So NO, H2, and H2O are placed in a container. These are initial amounts. Then the following equilibrium is established. Here's our equilibrium reaction. At equilibrium, so I'm going to underline this, at equilibrium, because whenever we want to solve for any equilibrium expression, we need equilibrium values. So A says calculate the equilibrium concentrations of H2N2 and H2O, and part B, calculate Kc. So I'm going to go through and label some things. Everything that's given to us up here, like I said, these are initial amounts. When it says that it's put in a container, those are initial amounts. That's what you're starting with initially. So when, I'm just going to write this over here. When you are given initial amounts and looking for equilibrium. So when you are given initial amounts and you are looking for equilibrium, anything equilibrium, equilibrium constant, equilibrium concentrations, we use what's called an ice table. An ice table is a visual way for us to represent changes in concentrations or changes in pressures. We're going to set up an ice table. We're going to look at what it looks like. ICE stands for initial change, and equilibrium. Sometimes I use a table kind of like this as I'm looking at stoichiometry. So for ice tables, kind of change color just to keep things a little bit separated. So for an ice table, just kind of the steps for an ice table. 1, you need a balanced equation. Now, will they typically give you the balanced equation? Yes. But I recommend, like in this case, I'm going to rewrite the balanced equation. So I'm going to rewrite it 2NO gas plus 2H2 gas at equilibrium with N2 and 2H2O. The reason that I rewrite the balanced equation is so that we can do the ice table right underneath. So the second step is to write and complete the ice table. Now this is where, when there were some questions on how do we use stoich with equilibrium, here's where stoichiometry is coming back in. Really, it's looking at the mole ratios. We're looking at mole ratios. So I'm going to go ahead and set up my ice table. This is what it looks like. Right under my balanced equation, I'm going to have initial, change, and equilibrium. Just write ice. So here's going to be my initial, here's going to be my change, here's going to be my equilibrium. The only reason that we need this, that we're using this table, is to figure out what we have at equilibrium. So over here, I'll add another piece of information. The only units that can go into an ice table that can go into ice table are aqueous. No, that's not a unit. That's a state of matter. But it's the unit for that. Molarity and ATM. Molarity and ATM. Those are the only 2 units that can go into an ice table. Because you're either working with aqueous solutions or with pressures, with gases. So let's look at filling this in. We look at initial, right? These are the initial amounts that we're given. Now remember, the only units that can go into an ice table are molarity or atmospheres. Because they're asking us about concentration. So you always want to read ahead a little bit. They're asking us for equilibrium concentrations, for Kc. We're going to be putting concentration into our ice table. It's going to be way more work if we switch everything to ATM and then we have to go back. Just put concentration into the ice table. Now they gave us moles. Moles, moles. I cannot put moles in here. I need molarity. Well, remember that molarity is simply moles over liters. They gave us moles in a 1 liter vessel. So 0.1 moles of NO divided by 1 liter is 0.1 molar. So I'm going to go ahead and I'm going to fill in the initial amounts. NO is 0.10 molar. Again, 0.1 divided by 1. H2, 0.050 molar. Again, 0.05 moles divided by 1 liter. And they also say that we're starting with some H2O. So the initial amounts that they gave us in this problem was NO, H2, and H2O. If an initial amount is not given, it is 0. The problem says nothing about starting with N2. It's 0. Sometimes you only have reactants initially. Sometimes you only have products initially, and sometimes you have both. Because then it's going to go ahead and it's going to shift to equilibrium. So now here's our initial amounts. Now they give us a piece of information that we can put into this table. They tell us at equilibrium, the concentration of NO, so at equilibrium, the concentration of NO is 0.062 molar. They're giving us one of the equilibrium concentrations. So we just need to see, what does this change have to be? What do I have to do to 0.1 to get to 0.062? Well, I have to subtract 0.038 molar. That's my change. I have to subtract 0.038 molar. This is where the stoichiometry comes in. The change is based on the stoichiometry. It's based on the coefficients. NO and H2 have the same coefficients. So after change here, I'm just, for us, for this example, I'm going to put stoich in parentheses. Normally when you make an ICE table, you're just going to do ICE, you're going to fill it in. I'm just giving us this reminder that the change row is actually based on the stoichiometry. Now the plus and the minus are dependent on the side that it's on. Because I'm using up NO, that means that NO and H2 are acting as the reactants. We're using up. So I'm going to put a minus for H2 and a plus for N2 and H2O. Since I'm using up NO, that means that I'm using up NO, I'm also going to be using up H2. And across the arrow, that's what I'm going to be forming. Now, because NO and H2 have the same coefficient, they're going to be changing by the same amount. And H2O has the same coefficient as NO and H2, but it's going to be increasing by the same amount. Again, it's increasing because it's across from the arrow. NO and H2 are the reactants, they're being used up. N2 and H2O are the products, they're being formed. Now the change of N2. The coefficient of N2 is half that of NO, or H2, or H2O. If the coefficient is half that, the change will be half of the others. Now if you're like, well, can I write it out? Can I do stoich? Sure. You can do 0.038 molar NO. For every 2 NO, there's 1 N2. You get the same thing. So if you'd rather write it out, you can. So once we have the change row, now we can calculate equilibrium. Right? Imagine like in a math problem. Right? We have a line here. We're doing this math problem. Right, so imagine that it's the math. You're subtracting or you're adding. 0.05 minus 0.038, 0.012, 0.019, 0.138. This is the most important thing. This is why we need the ICE table, to figure out how much of everything we have at equilibrium. Because the last thing to do for an ICE table, right, step 3, is to write the K expression. So I did KEQ because it could be KC, could be KP, and solve. So actually for part A, calculate the equilibrium concentrations, we just did that. Here's part A. We calculated the equilibrium concentrations because they came out of the ICE table. Here's part A. Those are all the equilibrium concentrations of the products and the reactants. Then part B, calculate Kc. Remember, get in the habit of writing the Kc expression first. They're all gases. They all can go right into the K expression. So the concentration of N2 times the concentration of H2O squared over the concentration of NO times the concentration of H2, and both of those are squared. Write the expression so that way you're making sure that you can look back and that you're squaring what needs to be squared. So when we plug in all of our values, N2, H2O, NO squared, and H2 squared. Again, make sure your math is also, you're doing parentheses on the bottom, or you're solving them separately. It's 654. Again, K does not have units. K is unitless, but this is greater than 1, which means products predominate at equilibrium. You have mostly products at equilibrium, which makes sense if you look, right, 0.138, high concentration compared to the reactants. If you want to make a note next to example 11, this is like numbers 11 and 12 on mastering. So numbers 11 and 12 on mastering. Just did MC for mastering chemistry. If you want to actually look right up above, example 9 is like number 9 on mastering. Example 10 is like number 10 on mastering. I didn't mean for that to happen, but it just worked out that it did. So that's kind of looking ahead at some of the numbers on mastering. So for this example, whenever you're looking at an example with equilibrium, we just want to make sure that we pay attention to, are the amounts that they give us initial? Are they at equilibrium? What might we need? So if we read this question, it says that a mixture of 0.2 moles of CO2, 0.1 moles of H2, and 0.16 moles of H2O is placed in a 2-liter vessel. Placed in a 2-liter vessel means those are initial amounts. So all of these amounts given are initial amounts because they are placed in a container. So moles, moles, and moles. These are all initial amounts. The following equilibrium is established, and they give us the balanced equation. Part A says calculate the initial partial pressures. Initial partial pressures. That means we're not going to do anything related to equilibrium. Initial partial pressures of CO2, H2, and H2O. So I'm going to give a little hint here. We need to use prior knowledge for this question. By prior knowledge, we need to think back to topics that we've covered before. Well, let's think about, they want initial partial pressures. They want us to solve for pressure. So let's think about what we have, what we're trying to solve for. We are given, in the problem, moles, so N. We're given volume. We're given the temperature. And we need pressure. So think about that for a second. N, V, T, we need P. Think about what we've used before with gases that we could use in part A. P, V, N, we always have R, and T. You can use the ideal gas law. So for part A, what we're actually going to do is use the ideal gas law. We have not gotten to equilibrium yet. Right now we're focusing on initial. So if we want to solve for pressure, we want pressure of each substance. I solve for this. P equals, divide volume over, nRT over V. Pressure equals N times R times T over V. So I'm going to solve for each one of these. I'm going to solve for the pressure of CO2. I'm going to solve for the pressure of H2. And I'm going to solve for the pressure of H2O. That's what it's asking for. CO2, H2, and H2O. Pressure equals nRT over V. Look at what we're given. We're given moles of CO2, moles of H2, moles of H2O. I'm just going to plug everything into the ideal gas law. If I look at CO2, 0.20 moles. R is always the same, 0.08206, because that is liters times ATM over moles times Kelvin. Temperature is already given to us in Kelvin. If it was given to us in degrees Celsius, we would have had to convert. And volume is 2 liters. So there's our setup for CO2. The only difference for H2 and H2O are the number of moles that we start with. So for my calculator, I do 0.2 times 0.08206 times 500. I divide all of that by 2. I'm going to keep it out to 4 sig figs, since that's what my initial information was given in. So the pressure of CO2, the initial pressure of CO2 is 4.103 ATM. So H2, again, the only difference is the number of moles. It's 0.1 moles. Well, it's half of the number of moles, so we should expect it to be half of the pressure of CO2. 2.0515 ATM. There's H2. And then H2O, 0.16 moles was placed into a container. So 0.16 times 0.08216 times 500, all of that divided by 2, 3.2824 ATM. There's part A. There are answers for part A. Those are the initial amounts. Equilibrium loves using the ideal gas law. So when you look at what you're given, remember that the ideal gas law is how we can find pressure if we're given NVT, we need P. So part B, at equilibrium. So at equilibrium, I'm going to underline that, that's important. At equilibrium, the pressure of water is 3.51 ATM. Calculate the equilibrium partial pressures of CO2, H2, and CO. So let's look back at part A. Let's remember what we found and what might be useful. I'm going to do part B over here. In part A, we solved for initial amounts. Part B is asking us for equilibrium amounts. Well, remember that initial and equilibrium are part of an ice table. So for this, we're going to use an ice table. ICE stands for initial, change, and equilibrium. So if we have initial and we're looking for equilibrium, an ICE table helps us set everything up. So I'm just going to rewrite this equation right underneath here so I can set up my ICE table. So CO2 plus H2 is at equilibrium with CO. plus H2O. Ice table, we have initial, change, and equilibrium. I'm going to fill this in with a different color. So initial. Initial is what we just solved for. The only units that can go into an ice table is either molarity or ATM. Well, luckily we solved for initial pressure in ATM. So I'm going to plug in the initial pressures into the ice table. So CO2 is 4.103 ATM. H2, 2.0515 ATM. And H2O. So H2O is over here, 3.2824 ATM. Now we didn't solve for CO. It said nothing about CO initially. There wasn't any carbon monoxide put into the container. So its initial amount is 0. If it doesn't say anything about that substance initially, there's none there. So here's where this at equilibrium is important. At equilibrium, so in my equilibrium row, the pressure of H2O is 3.51 ATM. So now we want to calculate the equilibrium partial pressures for everything else. So what we need to do is we need to figure out how did we get from 3.2824 to 3.51? Well, we have to add something. You do 3.51 minus 3.2824. That is 0.2276 ATM. The change, you're either adding or subtracting. How do we get from initial to equilibrium? And looking at H2O, we had to add 0.2276 to get 3.51. You think about it like a math problem. Then the change row. This is the row that's based on stoic. So the change, and I'll make this note, this is based on stoic. It's based on the coefficients. Well, what are all of your coefficients? Coefficients for every single substance is 1. So all of the changes, the values of the changes are all going to be the same because they're all the same coefficient. But here's the difference. Remember, one side of the double arrow should be positive. The other side will be negative because one side acts as the reactants, one side acts as the products. Because we know that water had to add to it, we should also add to CO. So this side is our products, this side is our reactants. Because all of the coefficients are the same, they're all going to change by the same amount. And now we just do the math. Right, in the case of CO2, 4.103 minus 0.2276. H2, 2.0515 minus 0.2276. If you just used 4 significant figures throughout the entire thing, that's okay. I tend to go out to usually a couple more sig figs. And then CO, 0.2276. And again, this is all ATM. You can only use molarity or atmospheres in an ice table, and it needs to be the same thing every time. So this, because we were dealing in pressures, was all ATM. Here's part B. This is our answer to part B, this row. So by having the ice table, you can kind of just box that whole row or put an arrow or star it. But there's our answer to part B. And then finally, part C, calculate Kp for the reaction. Remember, the first thing you want to do if you want to calculate Kp, write the expression. These are all gases, so they're all included. But it's products over reactants. Pressure of CO times pressure of H2O over pressure of CO2 times pressure of H2. Write the expression first. You never know when you'll get points for just writing the expression. Then plug in your numbers. Products over reactants. 0.2276 times 3.51 over 3.8754 times 1.8239. None of them are squared because all of the coefficients are 1. So if you put this in your calculator, you multiply what's on the top, you multiply what's on the bottom, and you divide the two. I got 0.1130. I did 4 sig figs because that's what our information was. If you did 3, that's okay. But remember, K does not have units. So when you are given initial and equilibrium amounts, that is when you use an ICE table. Initial and equilibrium amounts, you use an ICE table. To plug into the K expression, it has to be equilibrium. So we can't plug in the initial amounts into the K expression because initial is not at equilibrium. Any questions on this example? Be able to get through one more. So this was the longer one of today. The next examples are just plugging back into K, not using ICE tables. Okay, so again, this was looking at initial and equilibrium and how we can use an ICE table.
So one side will always be positive and one side will always be negative.
Yes. One side will always be positive because you're adding, you're producing the products.
So will the products always be added?
Not necessarily.
So the reactants can be added.
You could, yeah.
But we always figure it out with
based
the
on
product
what they
first.
give you.
Okay.
Yes. Yep. All right. Example 12. At 100 degrees Celsius, Kc is 0.078 for this reaction. So think about what Kc means. Kc means we're dealing in concentration. You always want to pay attention to what K they give you. So Kc is concentration. I'm going to underline this. I'm going to make myself that note. But if we want to use this value, we have to use concentration. In an equilibrium mixture, that's important because that means we're already at equilibrium. So in an equilibrium mixture of the 3 gases, they give us concentrations of SO2, Cl2, and SO2. Then it says, what is the partial pressure of Cl2 in the equilibrium mixture? So this is actually a 2-step problem because they give us concentrations. Right, so first, it's at equilibrium. Right, I'm going to make myself this note. It's at equilibrium. So I'm going to say use Kc. They give us Kc. We know we're at equilibrium, so let's use Kc. Start by writing our Kc expression. C means concentration. I'm not going to worry about the specific unit that they want right now. I just know that I'm looking for Cl2. If I write my Kc expression based on the equation that they gave us, it's the concentration of SO2 times the concentration of Cl2 over the concentration of SO2Cl2. And I know that they didn't give us the states of matter here, but they said it's a mixture of 3 gases. So it can be plugged in. So if we look at this, we're given Kc, we're given the concentration of SO2Cl2, we're given the concentration of SO2. So we can start by solving for the concentration of Cl2. So if we plug in, I'm going to plug in all the values so we can see what we get for Cl2. So Kc was given to us 0.078. SO2 concentration, 0.052. We're solving for Cl2. We don't know what Cl2 is. SO2 Cl2 is 0.108. So in order to solve, we have to multiply 0.108 over. So 0.078 times 0.108, and then divide by 0.052. The concentration of Cl2 is 0.162 molar. Brackets means concentration. When you use Kc, this example is about using the equilibrium constant to solve for one of the substances. We're given the K, we're solving for one of the substances. Since we were using Kc, we solved for a concentration. Now the question says, what is the partial pressure? Well, now again, we're going to go back to a topic that we've talked about before. If it wants partial pressure, we want to deal in pressure. Look at the ideal gas law. PV equals nRT is the ideal gas law. What are the units for molarity? Like how do you calculate molarity, what over what? Moles over liters. So if I solve this for pressure, look at this, nRT over V. N is moles, V is liters. N over V is molarity. This is how we get P equals MRT, P MERT. Can't see the face I make when I say it. Right, capital M is molarity. If we need to solve for a pressure and we have molarity, we can use a derived version of the ideal gas law. Pressure equals, concentration is 0.162 molar, R is 0.08206. Temperature, they're trying to trick us. 100 degrees Celsius, we cannot plug Celsius into the ideal gas law. Has to be Kelvin. If you're like, I don't remember how to convert between Celsius and Kelvin, have no fear, it's on your equation sheet.
Have no fear. Wait, who says that? Isn't that like a...
I do that.
Now it's swaps.
Okay. On the equation sheet, under gases, liquids, and solutions, so it's on the back, K equals C plus 273. So it is on the equation sheet for you. So the temperature in Kelvin is 373. So molarity times R times temperature in Kelvin will give us the partial pressure of Cl2. So 0.162 times 0.08206 times 373, 4.266. I'm using 3. 4.96.
Okay, rebel.
And because R is liters times ATM over mole times Kelvin, well, your liters and your moles will cancel due to molarity. A cancels because of temperature. The pressure unit that we would have is ATM. So what this was, if we ignore what's in the red right now, this is using the Kc expression to solve for, in this case, one of the products at equilibrium. But then the question wanted us to take it a step further and go from molarity to pressure. So more of the examples that we look at, we'll look at this with using K to solve for one of the equilibrium concentrations or pressures. So example 13 says at 373 Kelvin, Kp is 0.416. Right, Kp, so now we're dealing in pressure. Always make a note of what you're dealing in. Are you dealing in concentration or are you dealing in pressure? So in this case, we're dealing in pressure. For this equation, if the pressure of NOBr and NO are equal, so I'm just going to start by writing pressure of NOBr equals pressure of NO. What is the equilibrium pressure of Br2? So let's just take a step back. We know we're dealing in KP. Let's just write the K expression. Let's write the KP expression out. KP, dealing in pressure, products over reactants. So NO and Br2. Pressure of NO squared times pressure of Br2 over pressure of NOBr squared. And it wants us to solve for pressure of Br2. But then they tell us if the pressure of NOBr and NO are equal, it doesn't matter what number they are. If this pressure of NO squared and pressure of NOBr squared are equal, what are these two variables going to do in this fraction? They're going to cancel. And if you're like, I don't know what they're going to do, just pick a number to make them equal. Make it 1. 1 squared over 1 squared, those cancel. These two values cancel out. They are equal. So if instead of pressure of NO, I plugged in pressure of NOBr, then you have pressure of NOBr squared over pressure of NOBr squared. They cancel out. Now we can solve for the pressure of Br2, because notice now Kp equals pressure of Br2. Kp is 0.416. Now we just need to make sure to include units. If we're dealing in Kp, more than likely it's ATM. The pressure has units. So this one, if you want to make yourself a note, is like 21, 22, and 23 on mastering. Right? There are questions similar to it. Now, is it a difficult question? Not necessarily. Does it require conversions? Yes. So for this reaction, it's given here, so it's already balanced for us. Kc is 55.3. Right? Kc means we're dealing in concentration. So if we want to use Kc, we have to use concentration. In a 2-liter flask, I'm just going to underline this and label it volume just in case, containing an equilibrium mixture. That means that all of these gases are already at equilibrium. There's no need for an ice table. They're already at equilibrium. There are 0.056 grams of H2 and 4.36 grams of I2. What is the mass of HI in the flask? Mass means that we should be solving for grams of HI. So if we look at this problem again, first they give us Kc. Second, they tell us that this is all at equilibrium. So there's no need for an ice table, but let's write our Kc expression. Kc, here's the equation. Products over reactants. C means concentration. So concentration of HI squared over concentration of H2 times concentration of I2. In order to use Kc, it needs to be in molarity. Molarity is concentration. I have Kc. I am solving for HI. The unit that I'm solving for I can worry about later, but I'm solving for HI. In order to plug in variables into the K expression, especially for this, it's Kc, we need to have concentration. They gave us grams of each substance. How do we find concentration? How do we find molarity? What over what? Moles over liters. So if I want to find the molarity, I need moles over liters. Well, notice they gave us a 2-liter flask, so the liters will be 2 liters. So what I'm going to do here, I'm going to solve for the molarity of H2, solve for the molarity of I2. I need to know the number of moles. Here's where the conversion comes in. 0.056 grams of H2. I want to go from grams to moles. Use the molar mass of H2. It's H2 gas, not just H. All right, so H2 is 2 times the mass of 1 hydrogen, so 1.008 times 2. 2.016 grams per 1 mole of H2. Now I need this. 0.056 divided by 2.016. 0.02778 moles of H2. Go out to at least 3 or 4 sig figs. Don't round too much. I would recommend just leaving it in your calculator if you can. So the moles of H2 that are in the container, 0.02778, divided by 2 liters, 0.0139 molar. There's H2. The reason that I'm solving for molarity is because in order to plug variables into KC, it needs to be concentration. It needs to be molarity. So I need to take the information that they gave us, and I need to make sure that I can go to molarity. So I need moles and I need liters. I know. 126.91 times 2. 253.82 grams for 1 mole of I2. Again, it's I2. Iodine is diatomic. Point 0.01718 moles of I2. Divided by 2 liters to get concentration, 0.00859 molar. So now we've solved for the molarity of H2 that's in the container, and we've solved for the molarity of I2 that's in the container. So now I can plug in what I have, right? I know that I'm solving for HI. The unit that I'm solving for, I'll worry about after I find HI in the K expression. So KC is 55.3. I'm solving for HI. I'm going to leave that as my variable. So times 0.0139 times 0.00859. Now we have to solve for HI. So the first thing I'm going to do is I'm going to multiply what's on the bottom over to this side. So 0.0139 times 0.00859 times 55.3. 0.00660 equals the concentration of HI squared. How do I solve for HI? Square root. Oh, I forgot to do that. Square root of my answer, 0.0813 molar. Now I'm not going to box it, I'm just going to underline it. There's my molarity of HI. Molarity comes out of the KC expression. What unit does it want for HI? Mass, once grams. So now we have to go backwards. Right, now go backwards. Right, go to grams of HI. I'm going to start with my molarity, 0.0813 6 moles over 2 liters. Times 2.1625 moles of HI. And we go to grams. So this question is really more stoic than anything. So 1.008 plus 120. Oh, I just got the answer, I guess. So 1.008 plus 126.91, 127.918 grams is the molar mass of HI. So the equilibrium part of this was this right here. Right, the equilibrium part was the part that's in red. The rest of it was stoic because in order to use Kc, it has to be in concentration. So I know this says for the rest of class, but this might be one way to help you review for the quiz tomorrow. Now the quiz is during the second period of class. We're going to do at least one quick example after the do now with particle diagrams. But the one thing that I would recommend, because there's no video for tomorrow, it's just reviewing for the quiz. In the practice packet, pages 3 and 4 in the practice packet are a worksheet that's called The Meaning of Equilibrium. Does a lot of review on writing the K expression, calculating K. What does K mean? Right, a lot of things that we talked about in the examples. I would suggest working through this. The answers can be found, so this is from Google Classroom. If you click on Unit 6 Materials, you have all of these different options. Right here it says Answers to Practice Packet. So there's a Google Drive folder, or you can go out to the class website. If you click on Unit 6 and you scroll down just a little bit, it has the practice packet and the Google Drive folder. So the meaning of equilibrium, pages 3 and 4 in the practice packet, will be a good thing to review for tomorrow. Then the beginning of class, we will do a little bit of review as well for the quiz.